Hi everyone. In this lecture, we will learn about theoretical analysis of space-time complexity analysis. Okay. So what we are going to do, we are going to learn about a notation which is known as a big O notation. So what this notation does, it basically provides us a mathematical notation to understand the complexity of an algorithm or to represent the complexity of an algorithm. So let us say we have an algorithm whose maybe time is some function of n. Maybe let's say the time is like a n square plus let's say bn plus some constant c. Let's say it follows a quadratic curve of this particular form. So how do we represent this function in the form of a big O notation? So it's very easy. In order to convert any function into big O notation, so what we do, we write a O followed by we ignore all the uh, we ignore all the you can say constants a b c x y z. We only are concerned about the value of n because time is dependent upon, like, time is going to shoot as the value of n is going to change. And also in n you can see there are two terms, one is n square and another is n. So we will take the term which has the highest power. So the highest power is n square, so we can say this is nothing but its order of n square. So this is how we are going to use this big O notation. And what it basically tells us, that in the worst case, whatever is the time complexity of this particular algorithm, let's say this is this curve a n square plus bn plus c. So it basically tells us in the worst case our time is not going to exceed the value of order of n square. So this can be written as, let's say, kn square, and whatever is the function, it can be written as it is going to have value less than equal to some kn square. Okay, for some value of k. Basically it tells us in any case the complexity of the algorithm is not going to be n cube, it's not going to be n4, everything would be below n square. Okay, so what we will do is we will look at certain common complexities that we will encounter. So we will discuss examples of order 1 complexity. This is how order of log n. So you can see log n is actually a very good complexity. It grows very slowly over the time. Linear is this order n log n is slightly higher, and order n square is pretty bad. N cube is more bad, and 2 raised to the power n is very bad. Okay, so we have exponential complexity for some examples. Like when you want to find subsets, they will end up getting a exponential complexity. Okay, and maybe you're finding the largest number in a sorted array, so that will have the least complexity, that is order 1. This is exponential. In between you will find order of n log n for some problems. Sorry, order of, let's say, n square, order of n square, which is better than 2 raised to the power n. We have order of n log n, which is better than n square. We have order of n, and we have order of log n, and we have order of 1. Okay, so in this order, so if you have a problem which can be solved in n cube, and maybe using some approach you can bring down the complexity to n square. Maybe using some approach, maybe you can bring it down to the order of n log n. When we talk about optimizations, the idea is to reduce the time complexity of the algorithm by using the appropriate data structure, or maybe by using a technique like sorting or searching. So when we are learning about data structure, we will also learn how to apply these data structures to bring down the complexity of problems. Okay, so now what we will do going forward is we will do theoretical analysis, and I will show you some examples how to analyze loop based code, how to analyze sorting algorithms such as bubble sort, how to analyze searching algorithms such as binary search, factorial, merge sort, polynomial evaluation, Fibonacci, and we are going to do all these examples one by one. So let's start from the next lecture.